thank you so much. It's wonderful to be here. There's only a few places in the world you can come. You can talk freely about things like spacetime asymmetry. This is one of them, and I'm so glad to be here. And so my talk today is going to be kind of like a little tour through some recent papers that I've written with my symmetry buddies. These are my buddies, Thomas, Hans, Jim. We've been having this conversation about spacetime asymmetry now. I don't know when it starts. I mean, I would put the start of it as maybe Jim's whole argument paper was the beginning, and then that got stuff going. Anyway, I think what I'll do today is kind of touch on a bunch of different things that have happened since that paper having to do with spacetime asymmetry. If you don't have spacetime symmetry buddies, I would highly recommend getting some. Because, I mean, this is so wonderful just to kind of like, every day we'll flip up your phone, who's a text? Oh, a text from Thomas about, you know, some math question. I love it. And this is a new direction for me. My work previous to this has not been concerned with this stuff, but I'm so happy right now to be working on this stuff. All right, so I'm going to discuss a bunch of different notions of spacetime asymmetry today. Hierarchy of levels, I'm going to focus on 3 levels. A weak condition I'm going to call rigidity, after something Bob Geroch talked about in the 60s. Something I call the giraffe condition, named after David Malamud, and then something very strong called the Heraclitus condition. Before I jump in, I'm gonna do some isometry basics, just to quickly review a few basic definitions. So when I say spacetime today, I'm going to be talking about a pair mg. Here, M is a manifold. It's got all the usual assumptions like it's connected, it's Hausdorff, it's smooth. G is a Lorentzian metric on M. Now, spacetimes mg and m prime g prime, I'll say they're isometric if there's a diffeomorphism from the first to the second, such that when you pull back the metric g prime, it just is g. And now, I want to say a global symmetry of spacetime is an isometry from the spacetime to itself. So this accords with the physics literature. This is the definition Wald uses in his book. It accords with the philosophy literature. This is how Irvine, for example, defines symmetry in his 1989 book. So the symmetries of Minkowski spacetime are going to include translations, reflections, rotations, boosts, all those sorts of things. So now I want to consider an influential construction due to Irvine and Norton, used in discussions of the whole argument. So let mg be a spacetime and let h and its complement have non-empty interiors. There is a whole diffeomorphism from M to itself, which is non-trivial in the whole, H, but acts as the identity outside of the whole. So hopefully we're all familiar with this whole diffeomorphism idea. It's immediate from that definition. We have this proposition here, given the definitions we've got on the table. Let mg be any spacetime and let psi be any whole diffeomorphism. Well, then if you take the original spacetime mg and you push forward that metric, well, those are going to be isometric, and C is going to witness that isometry. So here's the obligatory picture of this. We've all seen this. All right, now I have a quiz. Irvine, at the end of his chapter 2 of the book I just mentioned, has a quiz. It's a beautiful little quiz. You think you know something, and then you take the quiz, and you think, oh, wait a minute, this is maybe more subtle than I had thought. So here's my quiz. I've only introduced a few definitions. A whole diffeomorphism is always a spacetime symmetry, sometimes a spacetime symmetry, or never a spacetime symmetry. Okay, so hopefully you have an answer, A, B, or C in your head. I won't call on you, just, you know, or have you raise your hands for this or anything, but just hopefully you have your answer in your head. Now, you got the chance to change your answer. So this is kind of like the Monty Hall. I'm going to give you something, and let's see if this changes your answer. I'm not going to tell you where this came from. Maybe it came from a referee report or something like that, I don't know. But here's an idea floating out there. It's out there, I've talked to people, you know, they've said this to me. Here's something to think about. Consider Minkowski spacetime mg. Since the metric g is the same at every point, in this, what sense? Well, it can be isometrically mapped into any other point. The spacetime is flat at every point. We know that any whole diffeomorphism will be an isometry, and therefore a spacetime symmetry. Therefore, the answer has to be either A, always, or B, sometimes, because we have this counterexample in hand. So back to the quiz. Did this change your answer? Hopefully you are not tricked. Hopefully you knew all along the answer was C. A whole diffeomorphism is never a spacetime symmetry. Okay, so what I want to do now is, well, how would you prove that? If I said, okay, yeah, the answer is C, huh? Well, I want a proof. Give me a proof. Where's your proof? Well, I'm going to say the proof comes from, you'd invoke a general rigidity theorem from Geroch, 1969. And so I want to take a closer look at that now. So, rigidity. This is the lowest level of our hierarchy. And I'm going to use the whole diffeomorphism construction just considered to define this notion. That's not how Geroch does it, but it's how I'm going to do it. It's how me and Hans did it originally. Okay, so the condition essentially requires that when global symmetries of a spacetime are fixed in an open region, however small, they're going to be fixed everywhere. So the definition is this. A spacetime mg is rigid if for any open set O and any isometry from M to itself. If the isometry is the identity on O, well, then it's got to be the identity everywhere. So I want to emphasize again, this definition is a bit different from the one. It's less general than the one that Geroch uses. But the idea here is to work with automorphisms that act as the identity on open sets, or regions outside the whole. And this is going to help connect up Geroch's very general work that I think was ignored by philosophers for a long, long time, decades, and the whole argument literature. So here's the general result in his paper. So let mg and m prime g prime be spacetimes, and let v and v prime be orthonormal tetrads at points p and p prime respectively. Well, then there's going to be at most one isometry from m into m prime, which takes p into p prime and v into v prime. Very, very general. So one simple corollary of this general statement is the one that kind of now is more in the form of what you might find in papers on Horn. So let mg and m prime g prime be spacetimes and let O be an open set. If you have two isometries from m into m prime and they agree on an open set, then they agree everywhere. They're the same isometries. So taking mg to be m prime g prime, and then noting that the identity map is always an isometry, then we see that any spacetime is rigid, according to the definition I gave, and therefore it follows that the whole diffeomorphism is never a spacetime symmetry. So that's how you'd prove that statement. You take the general Geroch, and then you'd translate it into the language of that quiz. Okay, who cares about rigidity? And what does it have to do with the whole argument? I keep talking about these things as if they're related. So James Reed and Tushar wrote a paper where they object to Hans and me, and this is kind of their line. They're saying this has nothing to do with the whole argument. Okay, so I want to say a couple things. So for one thing, I want to say Geroch's 1969 general rigidity result is the big idea behind Jim's paper. just is. And when Jim wrote his paper, he said the following proposition, but he never provided a proof for it. He just said it. It turned out to be true. But here's a proposition that at least hundreds of people who have now cited Jim's paper think is related somehow to the whole argument. Let mg be a spacetime and let C be a map from M to M, which is a non-trivial whole diffeomorphism. Well, then you know that the identity map on M is not an isometry between your original spacetime and the one that you push forward. And so Jim uses this formal fact to go on and make an argument that because the identity map is not an isometry, you can't use it to compare these two guys and so on. You may disagree with what Jim has said, whatever, that's not really relevant to what I'm saying. I'm just saying, look, this is how rigidity really is related. Jim didn't talk about rigidity in his paper, but it's there. And so how would you prove this result? Well, you invoke the general corollary of Halvorson and Manchak. Since you know that the whole diffeomorphism, you've got that as an isometry, well then the uniqueness says that the identity map can't be an isometry. And so Jim, in conversation sense, he's fully acknowledged that his argument rests on the Geroch result in this way. It rests on this idea of rigidity. And indeed, recent discussions that Hans and I have had with him have culminated in some new papers on determinism that we think are also relevant to the whole argument. So that's where I want to go now. So I think now we have a more mature view of what we're doing, both Jim and Hans and I, and that's what I'm going to present now. So determinism, how is determinism related to rigidity? Well, I want to explore three definitions of determinism considered by Belot in his 1995 paper. It's a really nice paper because it just creates this nice little mini hierarchy of determinism conditions. It's very, very nicely done. So in order to do that, I'm gonna need the notion of an initial segment. I'm gonna need to focus attention. And so I'm gonna be speaking about globally hyperbolic spacetimes. So there's enough causal structure that's well behaved enough to talk about, something like an initial segment. And so I'm going to say that the time-like past of any Cauchy surface in any spacetime counts as an initial segment. And then here are the first two levels of Belot's determinism hierarchy. So de dicto here is the weakest. I have it at the top, but it's the weakest, and then this is going to be a bit stronger, and I'm going to consider a third one in a minute. But de dicto, let's take a look at that first. A collection C in H, so H is the collection of all globally hyperbolic spacetimes. A collection in H is de dicto deterministic if for any spacetimes in the collection and any initial segments U and U prime in these two spacetimes, if there's an isometry between the initial segments, then there has to be an isometry between the models themselves. Okay? De re is just like de dicto. The only difference is this little bit at the end here. So the only difference is that for de re determinism, we're going to require not only that there be an isometry from M to M prime, but that isometry is an extension of this isometry. Okay? So this is very subtle stuff. So let me try to illustrate the difference between these two definitions. Well, first a bit on names. The naming situation here is a fucking disaster. We have de dicto and de re. These are the names I use. This is what Neil Dewar uses in his dissertation and in recent papers. But de dicto was originally called DM2 by Jeremy Butterfield in his 1989 paper. Gordon calls it definition 1. Malia calls it Lewis's analysis. Pooley calls it D2. So everyone seems to have a different name for this thing. But I'm going to stick with de dicto. De De Rey, as far as I can tell, this definition was actually introduced in the Belot paper. I can't find anyone talking about De Rey before 1995. So he called it definition 2. Malia called it the second resolution. More recently, Kudek has called it DM2+, sort of like Jeremy's DM2, but with a plus. Okay, so those are the names. Now, what's the difference between these two? Well, I already mentioned that de re is going to imply de dicto, because de re just has that extra little clause on it at the end. So if de re is satisfied, de dicto will be. But the two definitions are not equivalent. And to show this, Belot presents a famous classical example due to Mark Wilson from his 1993 paper, where he considers a perfectly symmetric column that after a certain time collapses, right? Maybe you're familiar with that example, maybe not. Here's an example from general relativity, which essentially does the same thing. This example is essentially just a really simple type of analog for GR, right? So what I'm going to do is I'm going to take two-dimensional Minkowski spacetime, and then above that dotted line, I'm just going to delete everything above that dotted line. And so what that means is that there's going to be symmetries initially, and then later those symmetries are going to disappear. And that's really what's going on with the column. Up until a certain time, the column is just there, it's perfectly symmetrical, and then after a certain time, it falls in one direction. Here we have a direction picked out. One direction continues on, as it were, another direction kind of ends. Okay, so so I claim that this spacetime considered as a singleton collection is de dicto. It's de dicto deterministic, but it's not de re deterministic. So any singleton collection turns out to be de dicto, right? Because all you need for de dicto is a global isometry from the model to itself, if you just have one element. So anything will be de dicto if you're just looking at a singleton. But this guy's not de re. Why? Well, you can do a reflection isometry here and take any point tx into t minus x if you're just looking at this initial segment. But you won't be able to find a corresponding global extension of that isometry. Why? Because, there are asymmetries later on. And that's the problem. That's why this doesn't count as de re deterministic. Okay, so which collections of globally hyperbolic spacetimes count as de re deterministic? Well, consider the collection V plus of all four-dimensional, globally hyperbolic, maximal vacuum solutions to Einstein's equation. You need all four of these properties. If any one of these four properties is not there, you're not going to get it. But I claim that if you've got all four of those properties, that any subcollection of V plus is going to be de re deterministic and therefore de dicto deterministic. How do you prove that? Well, it's the Choquet-Bruhat-Geroch result there. Hopefully, I see a lot of heads nodding. So, famous result, connected to determinism in GR as we want to connect up our philosophical discussions to the physics, and this is what does it. So we have a sense in which GR is de re and de dicto deterministic if we're focusing on a narrow collection of really, really well-behaved spacetimes. Okay, now I want to look at this third definition that Gordon introduces, because something really weird happened. Gordon wrote this paper in 1995. He talked about these three definitions. The first two definitions, over the next 30 years, there's thousands of whole argument papers written where they talk about these two definitions. But no one in the world talked about this third definition. And we don't really know why, but we started to talk about it recently, and it has to do with rigidity. Okay? So here's the de re deterministic determinism definition here. here's Belot's third definition. It's exactly the same. The only difference is here I require that this isometry at the very end needs to be unique. So I don't just have existence of this isometry like I do in de Re. I require that this isometry that extends the initial isometry be the only one. Okay. So it's immediate that any collection that's de Re deterministic is de Re star deterministic is de Re deterministic. Belot introduces his own example to show that within the classical space-time context, the two definitions are not equivalent. I have my own favorite example, and that's Leibnizian space-time. So considered as a singleton collection, Leibnizian space-time is de Re deterministic, but it's not de Re star deterministic. So here's a passage from Irvine from way back, way before the whole argument, 1977, which Jim in his whole argument prehistory paper argues is the argument that eventually morphs into the whole argument. Okay, so if the history of the particle is represented by a time-like world line on Leibnizian spacetime, then determinism cannot hold. For among the automorphisms of Leibnizian spacetime are those which are the identity on the portion on or below some given time slice, but which differ from the identity above that time slice. Such a mapping leaves fixed the entire past history of the particles while changing their future behavior. And since the automorphisms of the spacetime should be symmetries of the dynamical laws, whatever they are, there's going to be two solutions which describe the same particle histories for all time, past times, but which describe different future behaviors. So whether or not Leibnizian spacetime ought to count as deterministic in some sense, I think it's an interesting question. If you want to read more about that, Stein has a paper. Jim has a paper on the prehistory where he argues that Irvine is misreading Stein, and I don't want to get into that debate here. In fact, let me just lay all my cards out on the table. I don't believe there is a single notion of determinism out there. There's a bunch of interesting ideas concerning determinism, and we can explore all of them. So this is a point that Neil makes in his dissertation, Oliver makes it. Chris Smeek and Chris Vutrick have a paper on determinism where they make the same point. I think Julius makes this. I mean, these are all my friends in this sense that we're all determinism pluralists. So there is no one definition. I'm interested in just mapping out which space-time collections are deterministic relative to which definitions. I think that project on its own is already of interest. And I think that it's of some interest that there exist definitions of determinism out there that are strong enough, and in particular the de Re star form, that are strong enough to capture Irvine's sense in which Leibnizian spacetime is indeterministic. So maybe you don't think that Leibnizian spacetime is indeterministic, like Irvine does. Maybe you disagree with him. Maybe when I was reading that quote, your stomach was just like, pushing back on that. Fine, it doesn't really matter to me. I'm just interested in the fact that there are these really strong definitions that aren't usually considered and that haven't been considered in the whole argument literature that are strong enough to count models that kind of, to some folks who have Hexaeus leanings, say they're indeterministic, but according to the usual definitions count as deterministic. I mean, that's essentially what Belot is doing in this paper. He's ratcheting up levels of determinism, and at every level he's pointing to models and saying, I feel in my gut this thing is not deterministic, but all the formal definitions that I've got here, they all say it is. And so he claims that it can't be a formal, there can be no formal definition of determinism. Getting ahead of myself a little bit, I'll make that point in a second. The culmination of the Belot paper is an example that seems to be deterministic according to his really strong de Re star form, but is indeterministic by the lights of certain Hexaeus positions. And that's what leads him to this notion that determinism can't be a formal property of theories. So here's his example. In this example, W is a world with spacetime points in a Newtonian spacetime structure. It initially contains a single alpha particle, and the laws of nature decree that after 13 years, at t equals 0, the alpha particle decays into a continuum, many beta particles, arranged so that at time t, the beta particles form a spherical shell with radius t, each beta particle moving away from the center of the sphere along the radius. So that's the example. And a global rotational symmetry of W takes the world line of one beta particle, call it beta 1, into the world line of another, beta 2, and the presence of such a symmetry, according to Gordon, supposedly allows one to make sense of the idea that beta 1 could have been beta 2. So, because beta 1 could have been beta 2, according to Belot and his gut, this has got to be an indeterministic setup, even though he claims it counts as deterministic, even according to the very strong Dirac star form. So that's what I just said. So in a recent paper, Jim, Hans, and we pushed back on this idea. So we highlight that Belot's all-important third example is actually as ambiguous as it's presented. One natural way of making the example precise does render it de re deterministic, like Belot claims. But another approach, which is consistent with him actually having names for the beta particles, beta 1 and beta 2, that actually renders it de re star indeterministic. Thus, we claim that Belot can't have it both ways. If it really is true that the example is indeterministic by the lights of certain hexaedis positions, then the example ought to be formalized with names, beta 1, beta 2. I mean, he uses these names in his argument for why it's indeterministic. But if names are involved in the model, then we claim that the example then it's false that the example is deterministic. It's indeterministic according to de re star. Okay, so now back to general relativity. Which collections in GR satisfy the de re star form? Well, the uniqueness clause in de re star, it's just the rigidity condition. In disguise, maybe. So you can combine the Geroch rigidity result with the Choquet-Bruhat-Geroch result. Those two results come together to prove that any collection of four-dimensional globally hyperbolic maximal vacuum solutions are going to be de re star deterministic. So this result shows a sense in which GR is actually much more deterministic than we had previously known. And so in addition to me and Jim and Hans, some other people who have started to write about this a little bit would be Klaus Landsman and Frank Kudek on recent papers. I think the five of us are the only people who have written about this yet, but I think there's something here that deserves our attention. I think GR is just more deterministic than we've appreciated, and that has implications for the way we think about things like the whole argument. That's what I'm going to argue. But for now, let me just say that stepping back, we see that Belot's de re star determinism is quite promising as a formal definition. Gordon doesn't even want to own this thing. It's great. It's awesome. I love this definition. It's great. It's strong enough to capture Ehrman's intuition that Leibnizian spacetime is indeterministic. The other lower levels don't do this. It's strong enough to capture Belot's hexaedis intuition that his third example with names is indeterministic. The other two don't. And yet it's weak enough to be satisfied by a significant swath of GR. Even so, I recognize that according to some extreme hexaedists, the de re star form may still be too weak. So I'm gonna return to discuss the extremists at the end of my paper. All right, so I'm now gonna bump up a level, just say a couple words about this middle level before moving on. The giraffe level requires that the global symmetries of spacetime be completely fixed. So a spacetime is giraffe if the identity map is the only isometry. So David Melliman said, well, here's a way to construct a giraffe spacetime. Just take Minkowski spacetime, remove a compact giraffe shape region from the manifold. So here's a giraffe spacetime. Minkowski spacetime has all sorts of symmetries. You've got translations and boosts and all sorts of things. But once you remove this, it's such a weird shape, right? Once you remove this, all those symmetries gone. Can't do anything anymore. Here's another giraffe spacetime that's going to come up in a bit. This is two-dimensional Minkowski spacetime with the origin here, and you remove everything except for this triangle. That will also get rid of all of your symmetries, but it's just a lot easier to work with than that giraffe thing. So I'm going to come back to this example in a minute. Of course, any giraffe spacetime is rigid. It doesn't go the other direction since Minkowski spacetime is rigid, but it's not giraffe. But here's something I want to emphasize. Virtually all example spacetimes that you've ever seen in your life, unless you've been reading some weird papers on giraffe spacetimes lately, you've never seen a giraffe spacetime. Because you open up any textbook, Wald, Hawking Ellis, whatever, every spacetime you're looking at is not giraffe. And yet everyone knows that giraffe spacetimes are actually generic in some sense. So to have global spacetime symmetries is actually really, that hardly ever happens. And yet it's the only sort of thing that we ever see. Some partial results are available on that, but a genericity result is still, it remains elusive. All right, so now I want to bump up to the final level, the strong asymmetry condition, the Heraclitus condition. So the strongest condition requires that the local symmetries of spacetime just be completely fixed. Not just global symmetries, but local symmetries as well. So here's a definition that came from a paper with Thomas from a few years ago. A spacetime MG is Heraclitus if for any distinct points P and Q and any open neighborhoods around those points, there's no isometry from one neighborhood to the other that takes P into Q. Okay? So, since any neighborhoods of any distinct points fail to be isometric, each event is unlike any other. Each point that you pick out has a completely different geometry than any other point. No two points have the same geometry. And so in such a spacetime, you might say it's impossible to step into the same river twice. Okay, so one can show that a Heraclitus spacetime is maximally impermanent in the sense that there are no local killing fields anywhere in any neighborhood of any point. Let's call this a model with that latter type of asymmetry of Buddha spacetime. So Buddha says everything is impermanent. I take that to be no local killing fields. There's change happening at every point. There's a paper that says Buddha spacetimes are generic. But what I want to emphasize is that Heraclitus asymmetry is strictly stronger than the Buddha asymmetry. So you can step into the same river twice, even if every event is impermanent, right? So how can that be? Well, it's actually even worse. A Buddha spacetime doesn't even have to be giraffe. A Buddha spacetime can have no local symmetries in the sense that it's Buddha, but it can still have global, discrete symmetries if these symmetries are non-continuous, if they're like reflections. And so I'm going to look at an example in a minute. So it's immediate that any Heraclitus spacetime is giraffe, but some giraffe spacetimes are not Heraclitus. This is an example of a giraffe spacetime, but it's sort of like maximally not Heraclitus, because you pick any 2 points, there's going to be open neighborhoods around these points that are going to be isometric. It's flat at every point, so. Proposition, Heraclitus spacetime exists. So I want to talk about this for a minute, because I said a moment ago, you've probably never seen a giraffe spacetime unless you've been reading some literature on giraffe spacetimes. I think it's good to get a grip, a concrete grip on certain examples, and so I want to jump into an example so we have a sense of what a Heraclitus spacetime is like. So I'm going to start with that triangle portion of Minkowski spacetime in tx coordinates. I'm going to call it mg. So I'm just looking at this little triangle. Remember, the origin is down here. This is tx, and I've just cut out this little triangle and deleted everything else. Now I'm going to introduce a function f that's the Euclidean distance away from the origin point. And then I'm going to introduce a conformal factor that's just 1 over that. So this conformal factor blows up as you approach the origin point, but it does so in this really nice way. I claim that this conformally flat spacetime is Heraclitus. It's really simple. It's Heraclitus, and I want to say why it is Heraclitus now. So you can do a little computation. The Ricci scalar comes out to be this number, which is proportional to the Minkowskian distance from the origin. So any local isometry must map a point P to a point Q with the same Minkowskian distance from the origin. So on this triangle here, if I'm looking at a point like here, and I want to preserve the Ricci scalar value, so there's a certain value that it's got here, I'm forced to map it somewhere on this blue line, because those are the only points that have the same Ricci scalar value as my original point. Now I want to introduce a second scalar q, defined by taking the derivative of the Ricci scalar twice and then taking contracting with the metric. So this is another invariant scalar curvature function. I don't know that it has a name. I looked around, I couldn't find a name for it. I just call it Q. If you know the name of it, I'd love to know what it is. But the point is that this scalar function Q, it's got to be preserved just like the Ricci tensor, or the Ricci scalar has got to be preserved. And you do the calculation, and it's proportional to both the Ricci and f, small f, which is the Euclidean distance from the origin. And so what that means is that if you're mapping any point into any other, you're going to have to respect that. So if you're mapping this point here, you're going to have to map it the same Euclidean distance from the origin. And so now you just combine the two results. There's only one place to map any point, and that's into itself. Okay, one can easily extend this spacetime in a symmetric way to produce that example that I was mentioning before, of a Buddha spacetime that nonetheless has global symmetries. So this would be an example. So this is Buddha. Every point is impermanent. Every point is changing. But there's a global reflection isometry that you just take any point tx into t minus x on that spacetime, and you've got an isometry that's not the identity map. Okay, so there's reason to think that Heraclitus spacetimes are generic, just like with giraffe spacetimes, just like with Buddha spacetimes. In fact, in the compact Riemannian context, there's a theorem. But Heraclitus spacetimes are highly structured at each point, allowing for some very strong uniqueness results. So let me just mention one here. Spacetimes mg and m prime g prime are, I say, locally isometric. If each point P and M has a neighborhood, it's isometric with some open set in m prime, and then correspondingly with roles of the spacetimes reversed. Definition: a spacetime property is local if given any two locally isometric spacetimes, one has the property if and only if the other one does. This note was more for the Oxford folks, just because Frank Geroch is now writing his paper where he's collecting a bunch of different definitions of local spacetime properties. I just want to say that of all of them, this one is the most liberal. It lets in more properties than any of the other definitions. And so it's usually the one you'd want to work with if you're going to prove the strongest possible theorem, because usually the form of your theorem is for any local property blah then blah, and so you want to go with this definition here, and the example coming up is of that form. So Heraclitus spacetimes, you can show, and this is kind of weird, they're locally isometric if and only if they are globally isometric. So given any collection of local properties, there's at most one Heraclitus spacetime with those properties. So it's a theorem and here we see why you'd want the most liberal definition of local. But here we see a theorem that is showing that local structure determines all global structure. All topology, the global topology, the global causal structure, which causal conditions does it satisfy, and so on. And this result can be applied in a variety of different ways. So here's one way you can apply this result. You can show that a widespread cosmic underdetermination problem completely disappears when you restrict attention to Heraclitus spacetimes. Why? Well, essentially because local observations can uniquely determine global structure. So another way to put the point, any result that relies on a certain type of cut and paste construction pioneered by Penrose, Geroch, others, it's gonna be ruled out by focusing on Heraclitus spacetimes. So this is because the cut and paste construction, usually the way you do it is you have copies of spacetimes and then you start cutting and pasting them together. And if that's the type of cut and paste you're doing in a lot of these theorems, that's what you are doing, you're going to introduce global asymmetries, but you're going to introduce local symmetries. So it produces spacetimes that are giraffe, but they're going to fail to be Heraclitus. So you can beat Manchak at his own little cut and paste game. You know, a lot of people want to point to some of these cut and paste things and say, well, that's unreasonable. And usually the way that they want to rule it out is by some kind of no-hole condition. But that's a really tricky road to start going down. And I could talk about that a little bit. But here's a really nice way to do it. Heraclitus spacetimes are generic. So in that sense, it's a really weak condition. I think almost every spacetime is Heraclitus. And yet it's very strong in the sense that once you assent to this condition, you can start proving all sorts of uniqueness results. And you can start ruling out constructions like this. Okay, so there's a great deal more to say about Heraclitus spacetimes. They seem to shed light on the relationship between symmetry, structure, and coordinates. So Thomas has been heading up a series of papers on that side of things. I'm not going to say anything about that today, but that's another use for this radical asymmetry. In the last 5 minutes, I'm going to focus on coming back to determinism. I'm going to respond, or kind of maybe respond, to the extreme hexaetist. So recall, this is someone who, even Gordon's highest or most stringent determinism condition, de re star, they look at that and say, if is that all you got? That's not strong enough to capture my hexaetist intuitions. This is the type of person I'm calling an extreme hexaetist. Warning, the following, it seeks to engage with metaphysical positions that are not clear, at least to me. So this is kind of like a bit, I don't know, living on the edge. This is dangerous for me, but I'm going to do it anyway. Maybe what I'm going to say is nonsense, but hopefully, even if it is nonsense, kind of like Wittgenstein, at the end, maybe it'll just click, and you'll see why the extreme Heraclitus is sort of misguided. My goal is to respond to extreme Heraclitus on their own terms. So according to some philosophers, even the de re form of determinism is not strong enough to capture a notion of full determinism at the heart of the whole argument. So whatever you're doing, and this is I think what Gordon was doing in his paper. This was the goal. He was, laying out all these definitions and saying none of these really are getting at the heart of things. Okay. So here's an influential definition along these lines. So this isn't really a definition, and so in a way, I don't even know what I'm saying here, but this is what you might find. I'm taking this from Oliver Pooley's paper, his handbook paper. Let's say a collection of spacetimes satisfies full determinism if for any spacetimes in the collection that intrinsically agree on some initial segment, the spacetimes intrinsically agree in their entirety. So Oliver makes the point, well, again, something about names. Again, this is a disaster. So this metaphysical form of determinism goes by many names. It's called de re, unfortunately, by Hawthorne. It has nothing to do with the de re that Neil discusses. Pooley calls it det one. Tittle calls it full. I'm going to go with full. And in the paper with Hans and Jim, we go with full. So, as noted by Pooley, it seems that the anti-Heraclitists will judge full determinism to just be equivalent with de dicto determinism. So intrinsic agreement just is isometry. There's nothing more to it than that. And so then the definition just collapses to de dicto. But to the Heraclitists, they will judge full determinism to be a strictly stronger form of determinism than de dicto. So Halvorson, Manchak, and Weatherall argue that the Heraclitists can only make sense of this intrinsic agreement in the definition of full determinism by considering sufficiently enriched theories in which spacetime points are named. You got to name your spacetime points. And so Hans gives a nice definition, a formal definition of this type. Okay. Now, due to the possibility of symmetries, collections of general relativistic spacetimes won't have names like this in general. But each point in a Heraclitus spacetime is effectively named, since isometries, even local isometries among Heraclitus spacetimes are unique. So you look at any point in Heraclitus spacetime, it's going to have a unique set of metrical properties that are going to be distinct from any other point. And you can just take that as its name. So in that sense, it's effectively named. So a collection of Heraclitus spacetimes will have sufficiently many names to make sense of the ambiguous intrinsic agreement given in the definition of full determinism. And indeed, we show a proposition that says, if you're looking at any Heraclitus subcollection of V+, now we don't actually know if this is an empty set. Presumably, the Heraclitus spacetimes are generic in V+, but this is an open question about, well, are there even non-empty collections here? So I would love to know more about that. But any collection that is Heraclitus and a subcollection of V+ is going to satisfy this incredibly strong definition, full determinism, this metaphysical type of definition. That's what we claim. Thus, even by the lights of extreme Heraclitists, a significant swath of general relativity is deterministic. Thanks.